So following on from the previous video, we were trying to sketch this function here, and then we got to this stage here. So this is our graph so far. So now let's look at the second derivative. We suspect that the second derivative will be 0 at pi over 2 because the gradient here is 0, and then we suspect that the gradient here will also be 0, and so on here. Okay, but let's double check everything. So start out with your f of x. So this is your original function. Differentiate it. So it's you using the chain rule here. So differentiate this, it will then give you this. Tidy up, and it will give you this. So the next thing to do is ask yourself, when will the gradient be 0? So this is when will the gradient be 0? So when will this be 0? Well, this would be 0 when, well, concentrate on making this 0, because if you have 0 divided by, let's say 3 or whatever, it would be 0. 0 divided by 2, that would be 0. So concentrate on making this 0. But then so this thing here will be 0. Well, hang on, cos will look something like this. Okay, so this here is 2 pi. This here is pi. So this bit here is pi over 2. You see, this thing here, this thing here would be 0 at cos pi over 2. Now just make sure that this doesn't equal 0 at pi over 2. Otherwise it would be 0 over 0. So when you look at the sine graph, it will look like this. This here is 2 pi. Pi will be here. Pi over 2 is 1. Pi over 2 is 1. So this is okay. So this thing here will be 0 when x is pi over 2. Okay. So the gradient will be 0. So this statement here is saying the gradient will be 0 when x is pi over 2. So what that means, what it's saying is, looking at that graph here, it's saying the gradient will be 0 when it's pi, when x is pi over 2. Okay, so now we need to check that at x equals pi over 2, f of x, so that's the original function, f of x does actually cross at 0. So let's double check. Okay, so now we know the gradient will be 0 at pi over 2, but let's double check that the actual function itself will be at that. Let's just check that the coordinates at this point will be pi over 2 comma 0. Let's just check that it is indeed 0. Okay, so we need to put this into the original function. So put pi over 2 into the original function. Put pi over 2 into the original function, and it does indeed equal 0. Check that for yourself. Okay. So we know that it cross. So we know the coordinates here will be pi over 2 comma 0. Okay. Now let's look at the second derivative, just to make sure that there's no hidden point of inflection anywhere between here and here. Okay, so let's look for inflection. Let's try and detect inflection points. So to detect inflection points, we need to look at the second derivative. So rewrite your f prime here. So hang on. So originally f prime was this, but let's rewrite this as this, and then we can differentiate this. So f double prime will be this. Okay, so looking at this here, visualize it as this. Visualize it as one block multiplying another block here. So the product rule is differentiate this, leave this the same, and then later leave this the same, differentiate this, and then it should give you this. Okay, tidy up, it will then give you this, and then this thing here is in effect 1. So here you've got minus 1 here, minus 1. And then rewrite this thing here as this thing here. So looking at this, f double prime here equals this. Now if you look at this here, you've got something squared. Well, something squared will always be positive. So you've got negative 1, take away something that's positive, that will always be positive. Then f double prime will always be negative. Okay, so f double prime equals this thing here. But then if you look at this thing here, you've got something squared. Well, something squared, the lowest that this could be would be 0. because if you have 0.003 squared, well, the point is that this thing here will always this thing here will always be positive because you've got this squared here. So you've got -1, take away a positive number, so that will just take the -1 further negative. Okay, so overall we can say that f double prime will always be less than 0. So if f double prime is always less than 0, then it's always going to concave down, okay, concave down. So f double prime is always in this region here. F double prime is less than 0, meaning it will always concave down. Okay, and then if you get a graph plotter and plot your f of x, plot your f prime of x, and plot your f double prime of x, it will give you this graph here. Okay, so hang on. So if you get your graph plotter and plot these three graphs here, it will give you this. It will give you this. Hang on. It will give you this. Okay. So sorry. So this here is our original function here.